Welcome to part 22 of a lecture on designing organic syntheses. Subject of today are two target molecules, both of them hydrocarbon terpenoids. Well, and the first one we will discuss is the so-called Longifolene. Obviously, sesquiterpene with 15 carbons in its skeleton. Well, and a bicyclic structure here and a bridge there. Here we see an isomethylene group. Well, it can't isomerize to the endo olefin, since this is forbidden by Brett's rule, as you know, with a double bond at bridgehead position. Well, okay, let us start with an exercise. Please try to figure out basic steps for the retrosynthetic analysis. So first step in this retrosynthetic analysis should focus on that isomethylene group, since this is, well, the only functional group and therefore, of course, the most sensitive one, should be introduced in the last step. Well, as I already said, we don't have the problem that the olefin could migrate to the bridgehead position. However, under acid catalysis, we would have a protonation here. Then we could have a cation there, and with this cation, Wagner-Meerwein type rearrangements could occur, which are frequently observed at the norbonane skeleton and related compounds. So it makes sense to get rid of that olefin in retrosynthetic analysis. So the first step is thinking about the transformation here, having a carbonyl there. A Wittig reaction should be rather reliable. To get to this structure. So, for the next step, we need somewhat more fantasy. Well, at least what we have learned, there is a six-membered ring. And six-membered ring we could set up by, for instance, a Diels-Alder reaction. So, that means in the next step we would have, or could, introduce an additional double bond for setting up a cyclohexene moiety as retron of a Diels-Alder reaction. However, disconnection here and there would then give a ketene as the dienophile. As we already know, that doesn't work. Ketenes usually give 2+2 cycloaddition as the result. However, in one of the first lectures or lessons of this lecture, we already learned that we could have another functional group, which is for the Diels-Alder reaction, which is then easily transferred into a ketone. Well, and an idea could be this one. Having a cyano group here and a chloride there. Hydrolysis here, well, replacing the chloride by a hydroxy group, then we have a cyanohydrine, and this could then decompose in equilibrium, giving the ketone. So, retro-Diels-Alder reaction as the next step within our analysis. Could lead us to this structure. So, this is, of course, indeed a simplification. However, setting up that moiety, especially this bond selectively without the isomerization of the olefins to the higher substituted position, well, this is a problem which one could address. So, but nevertheless, question mark. But one should keep in mind that the Diels-Alder approach is feasible. Well, we later on will see a synthesis making use of a Diels-Alder approach. But at first, let us discuss another idea which led to a complete synthesis by E.J. Corey's group. So, Corey envisioned that, well, one could disconnect here, having donator reactivity at this position and acceptor reactivity at this position. So let us draw the corresponding synthon . Donator reactivity here and acceptor reactivity there. Donator reactivity at this position corresponds to the natural reactivity of the enolate. For the acceptor reactivity, Corey had the idea that an alpha-beta unsaturated ketone could be here. Of course, this is only possible if we don't have a tertiary center here. Therefore, he has to eliminate one methyl group there and introduce a carbonyl group there. So, So cyclization, cyclization by a Michael addition process. Secondly, a methylation alpha to that carbonyl group. And later on, one has to get rid of that additional carbonyl group by some reduction method. Well, I have forgotten in the structure the methyl group here. So let's add the methyl group there. Next idea, we have annihilated 6 and 7-membered ring. Maybe one can build up the 7-membered ring by a ring enlargement reaction starting from a 6-membered ring. So, in this case, following this idea, we get to this starting material for a several step transformation, and identifying this as an easily accessible structure, then we can say, well, okay, this is somehow a bidirectional analysis. We would like to start with that because we can easily get to this. I hope everyone notices how you would build that up by a Robinson annihilation, of course. Typical structure for a Robinson annihilation. So, what do you have to apply as starting components? With methyl, cyclohexane, hexane dione, and well, this alpha beta unsaturated ketone. Actually, this structure is very well known and has a name. It's the so-called Wieland-Mischer ketone, very well known as one almost starting component for several steroid syntheses. So, with this, well, basic retrosynthetic analysis in mind, we should now have a look at the real synthesis that the Corey group was undertaking. So, again, starting from well, sorry, there is one mistake in there. This is not the Wieland-Mischer ketone. This is the Wieland-Mischer ketone, and one has to start, of course, from methyl vinyl ketone. We will soon see or notice how that methyl group is introduced. Okay, so Wieland-Miescher ketone. First, acetalization with ethylene glycol catalyzed by paratoluene sulfonic acid. Introduces the acetal rather selectively for that carbonyl group, 66% yield of that alpha-beta unsaturated ketone, having the carbonyl group here. But we directly add the Wittig reaction already for that transformation. It wasn't done as a one-pot reaction. 66% yield of that was isolated, and this diene system then with 96% yield, of course, as a mixture of cis-trans stereoisomers here. With osmium tetroxide, the bis hydroxylation succeeded. And now it already becomes clear, I hope, for everyone, how Corey was planning the ring enlargement by a pinacol-pinacolone rearrangement. So, you need the leaving group here. You have selectively transformed the secondary hydroxyl group into a leaving group. Well, no problem, because this is sterically more hindered. Therefore, the combination of paratoluol sulfonic acid chloride, pyridine as base, will lead to this intermediary tosylate, which already under rather moderate conditions will eliminate paratoluene sulfonic acid with that migrating vinyl group, and therefore we get to the 7-membered ring product this one. %48. Next step, well, with two normal or 2 molar HCl in ethanol at 100 degrees, this acetal is hydrolyzed. And partially the olefin is already migrating. Nevertheless, most of it is still located here. And you see, during this reaction, here is the additional methyl group already. So, this transformation, just 100%. The next step is the crucial one. With potassium T butoxide, it's deprotonated here, conjugated then to that olefin, and it's reprotonated, then you have alpha beta unsaturated. In the same reaction flask, when you have that alpha beta unsaturated, you can also deprotonate here and get this as a nucleophile reacting there. Okay? All in one pot, unfortunately with a lot of possibilities for competing reactions, of course. Well, but nevertheless, the initial idea works. You get to this structure, you can isolate that with a 20% yield. Not a good yield, but the idea works. So, next step, I won't draw the intermediary structures anymore, is the methylation. You have to get in that, at this position, the additional methyl group. Well, then I have to add that the Wieland-Miesche ketone went into this process as a racemate. You might know the other structure with a 5-membered ring. Yeah, you can easily, here with a 5-membered ring there, you can easily get that by organocatalysis with proline with 95% EE. Unfortunately, this doesn't work that well targeting the Wieland-Miesche ketone. To my knowledge, there is then 75% EE. Maybe meanwhile in the last 10 years, where the field of organocatalysis has rapidly developed, there has been some improvement. However, at that time, it was necessary to separate the enantiomers. And that was done at the stage of the compound having the two methyl groups already at this position. So, resolution of the enantiomers, which of course then loses a lot of material. Third, hopefully reductive, reducing this selectively, maybe having to protect that, and therefore a third step and a fourth step, a couple of steps to get to the hydrocarbon. Yeah. After all, they got then Longifolene and isolated that in an amount of 17 milligrams, while having started with 20 grams of a Wieland-Miescher ketone. Well, they might not have applied all the stuff in every step, yeah, but this is a fact. They started with 20 grams and had 70 milligrams of that. Telling us that it is a nice idea, but still Longifolene is far better isolated from nature. Far more easy, okay? So, next example for an approach to Longifolene. That is the Diels-Alder approach. The leading scientists Xing Yang Liu in 1992. He was, at that time at least, at the University of Alberta in Edmonton, Canada. So, and the Diels-Alder approach was making use of an interesting intermolecular Diels-Alder reaction. Of this structure, well, okay, you can easily get this structure by a condensation process between cyclopentadiene and acetone. And these type of structures are called fulvenes. This is a fulvene, dimethylfulvene. Cheap compound Diels-Alder reaction with maleic anhydride. Toluene, 100 degrees, 24 hours reaction time. This gives then rather selectively the exo Diels-Alder product. You know, the endo product is a result of secondary orbital interactions with the electron density of the diene. Well, here we have also some additional electron density, electron-rich part. Well, this is the result. The exo in second exo Diels-Alder product in 67% yield compared to the endo Diels-Alder product in 0.25%. So, the Liu group was in need of that, targeted for that. And now, a couple of steps. First, treating this with 50% sulfuric acid for 48 hours at 20 degrees. What happened? It is protonated at that carbon. Then you have a tertiary cation here. This is the electrophile which indeed, which indeed gets close to the free electron pairs of one carbonyl group. Either this or that makes the both enantiomers. And here, by protonation, of course, the hybridization is changed from sp2 to sp3. So that makes sense. As I said, protonated there, tertiary carbocation there, cyclization, while having the acid moiety there, but I will draw it already as an ester, because secondly, methanol acid catalysis, esterification, and, well, third, already the hydrogenation. Let's wipe out that double bond. Therefore, this is hydrogenated. Overall yield through these 3 steps is 50%. Not bad. Now, basic reaction conditions. Methanolate in methanol. Epimerization will take place here. Yeah, okay, let's draw that again. Next step. This is treated with phosphor pentoxide and trifluoromethane sulfonic acid, rather acidic conditions, dichloromethane, some pressure, cause otherwise can't get to 65 degrees. And this results in the transformation to this structure. We have a CC bond formed. thinking about, is that correct? No, here we have it. Okay, this is correct. (82% yield). Of course, we should now try to understand what is going on here. So, if you eliminate here, you have the olefin. Okay? So, and then, under these conditions, highly acidic with phosphorus pentoxide, you will get an anhydride there with this carbonyl group as highly electrophilic. And this highly electrophilic one will then attack the the olefin. Okay? Electrophilic attack at the olefin. Similar to a Friedel-Crafts type reaction. Well, in this case, I think you would call that an ene reaction. Okay? If you figure it out in detail, the mechanism. So, but I think one can rather easily understand this type of reaction, and it works indeed very well. So, now getting in the other methyl group, that's simple, with an organocuprate. (96% yield). So, we will now discuss just two more steps. Then we have at least the framework of the final Longifolene. We treat this compound with a diazo reagent, diazo acetic acid ester, to be easily synthesized starting from glycine ethyl ester. So, and what you now are able to perform is, well, a Terpenoid reaction, a Terpenoid ring enlargement with this additional ester groups. Up to now you have always learned that with diazomethane, but it also works with a stabilized system like that. Okay, what's Terpenoid? This is the nucleophilic center, attacks the carbonyl group. Then you have the O- there and have an nitrogen leaving group there. Nucleophilic replacement with ring enlargement. Yeah? Hope you still remember the Terpenoid rearrangement. Well, maybe I should draw the result. you get a mixture of this plus the isomer, where you have to change the position of that ester and the carbonyl group. Well, this is a good result. You get that with above 90% yield. Next step is the hydrolyzation of the ester. Then it decarboxylates because it's a beta keto ester. And well, for the Longifolene synthesis, you don't have to care about the position of that carbonyl group because you have to get rid of it by reduction anyway. Okay? So, a couple of more steps are necessary, of course, but well, in principle, you have already set up the Longifolene structure, while you need an additional methyl group there, of course. So, okay, enough about the Longifolene. Always having that problem that getting rid of the carbonyl groups and completing the reaction sequence, you will lose a lot of yield there. So, therefore, let's have a look at a very renowned synthesis of another terpene called Isocomene, synthesized by Michael Pirung's group, published in 1979. This is the target. So this is Isocomene, and this synthesis by Pirung is so renowned because it succeeded in a rather high overall yield. So, retrosynthetic analysis. The idea, again, is making use of, well, a ring enlargement at the same time the second ring gets smaller. Okay, we know these type of reactions. Again, pinacolone rearrangement type processes. Okay, let's see. Or not pinacolone, just Meerwein rearrangement in this case. So, basic idea is we have two annihilated 5-membered rings. There is another one here. With a carbocation there. H plus eliminates. So, and this carbocation could derive from a rearrangement having a 4-membered ring here, a 6-membered ring there, carbocation at this position, it's simply the migration of this electron pair. That's it. Should be no problem. Especially because, well, you get rid of the highly strained 4-membered ring. 2 5-membered rings are, of course, in terms of ring strain energy, far better than a 6-membered with a 4-membered ring. Okay? So, having olefin here, just treating that with an acid. Just treating this with H+ should directly transform it, make the transformation to that target structure. So, and now one could analyze this one here. Of course, we would introduce the carbonyl group there in the next step in retrosynthetic analysis, having a carbonyl group there. Okay, so, and cyclohexanone with an annihilated 4-membered ring. How would you introduce the 4-membered ring? By a 2+2 cycloaddition process, of course, making use of photochemistry. Okay. So this is the basic retrosynthesis. So let's draw that. What you need is something like that. Okay. So let's see how the synthesis worked in reality. Starting from this simple substrate, which of course derives from that dione, which we were already noticing today as a starting material for the Wieland-Miescher ketone. So, with LDA, methyl iodide, additional methyl group has been introduced here. Yield 81%. Next step, a Grignard reagent. So, nucleophilic center will react with this carbonyl group. You then have the alcohol as an intermediate. I will write it down because it's then more easy to follow that synthesis. After hydrolysis, you will have this intermediate And this is highly sensitive during hydrolysis because under acid catalysis this turns into the OH group, turns into a leaving group. HCl, again H2O, heating it up a bit. Will lead to this functionalized product with a 90% yield. So, now, next step, I should write that at the next blackboard is the photochemically induced cyclization. Highly diastereo selective, 77% yield of that, of course. This is a racemic synthesis, but highly diastereo selective. So, Wittig reaction introducing the exomethylene group. Let's call this structure A. Then we already have A. Then treating it with para-toluene sulfonic acid, heating it up, and indeed the reaction to give isocomene, then the final rearrangement succeeded in 98% as already written to the blackboard. Of course, it's a racemic synthesis. However, indeed, really impressive. So let us count. Well, you can buy that. Let's assume we have bought that. Yeah? So then, first step. Second, this is not isolated. The third step. Fourth, fifth, and after 6 steps, all in high yield, the synthesis was done. Well, indeed, highly impressive. Next lesson will take place on next Friday. We skip tomorrow. Subject of Friday will be, of course, also natural product syntheses, but we will focus on free radical reactions as a key step in these syntheses. Thank you for listening. See you next Friday.